A tempo synchronized echo effect is just like other types of echo effects, except the length of the time delay is relative to the tempo of our song. This way, the repetitions that are created line up with the rhythm of the performance. Typically, we're going to select some note, like a quarter note, an eighth note, a dotted eighth note, for the duration of our delay. To do this, we need to go through a conversion process. We start out with units for our tempo, typically in beats per minute, convert that to the length of a note, maybe in seconds or milliseconds, and then convert that length to a number of samples of delay. This will make it possible for us to index our signals at the appropriate time sample in the past. So let's go ahead and open up Matlab and go through the conversion process to create a tempo synchronized echo effect. Here in Matlab, I'm going to make use of some of the code we created previously for the feed-forward echo, and now I'll demonstrate how we can have a tempo synchronized delay time. At the beginning of the script, I import in a sound file. This is an acoustic guitar recording. It just so happens that the performance was recorded at 103 beats per minute as the tempo. That'll be important information for us to work with. Down here at the end of the script, this is where I'm actually implementing the effect, where I'm indexing some arrays as my method to create the echo. The part that we need to focus on and change is actually where we go through the process of calculating the delay length. Before, all we were doing is converting from units of seconds to units of samples. Now, when we go through this tempo synchronized delay time, we're going to have to go through several more steps. That's because the information we start out with is beats per minute as our time units. This is given as 103. So if you had a recording at a different time units or tempo, you would just put that in there. Tempo of the song. Now we'll go through several steps so we can eventually get to the appropriate number of samples of delay. Now typically, it's easy for us to convert number of seconds to number of samples. So what we'll do first is convert minutes over to seconds. So we'll put in, we have some number of beats per second. This is going to be based off of number of beats per minute. In this case, we're actually going to divide by 60. That's because we know that for every 1 minute, there are 60 seconds. So I'll put in our conversion over here. We had beats per minute. And then we multiplied by number of minutes for every 60 seconds. So dividing by 60 or multiplying by 1 over 60. So now we've got beats per second. When we're actually doing this delay, what we're more interested in is the number of seconds per beat, or in usually the case, it's the number of seconds per note. So we'll just take the inverse for now. So we'll say seconds per beat is equal to 1 divided by our beats per second. Now, important thing I'll point out is that when you're working with different time signatures, you have to be careful about which note is actually equal to a beat. If you're working in a common 4/4 time signature, then a quarter note is equal to this unit of a beat. But if you're working in an odd time signature or 6/8, then you'll actually have to be careful about making sure that the eighth note is equal to the beat. So for now, I'm going to put in here another variable that we'll make use of, and that's going to be our note duration. This is so that if we want, we can have a quarter note delay, an eighth note delay, a 16th note delay, and so on. So I'll put in that if we have a value of 1, that's going to be a quarter note. If we have a value of 0.5, it's going to be our eighth note. 0.25 would be our 16th note. We could have a value of 2. That's going to be our half note. They're just multiples then based off of the length of your beat. In our case, it's a quarter note. You could even also do things like a dotted eighth note, where you'd have an eighth note is 0.5, a dotted eighth note would be 0.75. So you can get as creative as you like there. So let's put in a variable here, note duration, is equal to 1. And we'll come back and we'll change some of these things later on. So the last thing we need to do is convert what we have here in seconds over to samples of delay. Here, it's going to be based on several things. We'll use this note duration to change the length of seconds per beat. So if it's just 1, we're going to keep that we have a seconds per quarter note in that case. Then we're going to multiply by our seconds per beat. And the last thing is to convert units of seconds here to samples by multiplying by our sampling rate, which is samples divided by seconds. So those parts will cancel. Lastly, there's an important thing for us to make sure that we're careful about, and that is we need our samples here to be integers. We're going to be indexing arrays. So if this calculation ends up with some fraction of a sample, that doesn't help us because we can't index that out of our array down here for our input signal. So I'm actually going to go through a process to round this. I'm going to make use of this rounding function called fix. Okay, so we've been able to start out with beats per minute, put in some note duration, and figure out the number of samples of delay. Now when I run this script, what should happen is we should be able to hear our feed-forward echo get created and have the repetition line up synchronized with the recording. Now let's try different note durations. Let's go with 0.5. How about the dotted eighth note, 0.75? And lastly, the half note, length of 2. So that's how we can create a tempo synchronized time delay to be used in any of our different echo effects.